Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 3rd, 2026, about 4 days ago. It demonstrates a surprising paradox where a binary large language model critic with strong offline accuracy, specifically an AUROC of 0.94, can actually cause a severe 26 percentage point collapse in performance during deployment. The paper is titled, "Accurate failure prediction in agents does not imply effective failure prevention." And as we'll see later, the proposed framework for testing these interventions could save developers a lot of wasted compute. So to formalize exactly when interventions help, the authors present this outcome matrix. The rows show the baseline result, and the columns show the result after intervention. The most important variables are C, representing recoveries where the model fixes a mistake, and B, representing disruptions where it breaks a correct solution. These counts feed into the equations below, defining the recovery rate R and disruption rate D, which quantify the trade-off between fixing errors and causing new ones. Now, Figure 1 puts those variables to work in a practical decision tree. The process starts in Step 1 with a small pilot study, maybe 50 tasks, to empirically estimate the recovery and disruption rates. Step 2 then calculates a personalized threshold, called P-star. The decision rule at the bottom is strictly quantitative. You only deploy the intervention if your model's current failure rate is higher than P-star. The worked example on the right shows this for the ALF World benchmark, where the high failure rate justified deployment and resulted in a net gain. Alright, having established the framework, Table 1 validates the critic model's own performance on held-out tasks. The first column lists the 3 different agents being critiqued: Qwen 3.8b, GLM 4.7, and Minimax M 2.1. Across all these systems, the failure predictor is remarkably precise. The bottom row reports an overall AUROC of 0.94 and an F1 score of 0.96, which proves that the critic is effectively learning task-agnostic failure signals rather than just overfitting to one specific model. With a strong critic in hand, the next step was choosing where to test it. Table 3 lists the 3 benchmarks selected to cover a wide spectrum of difficulty. At the top, Hotpot QA represents a high success regime, where baseline models already solve about 50 to 70% of tasks. In the middle, Gaia serves as a median success setting. And at the bottom, ALF World provides a low success environment, with success rates as low as 6%, meaning failures are the norm rather than the exception. Table 4 reveals the critical results, and the contrast is striking. Looking at the high success Hotpot QA section at the top, we see mostly negative outcomes. Specifically, notice the Minimax M 2.1 row, where intervention causes a massive regression of over 25 percentage points. The middle section for Gaia shows a similar pattern, with interventions hurting every model. However, the story changes in the low success ALF World section at the bottom. Here, because failures are common, the interventions finally pay off, giving a modest boost of nearly 3 percentage points for the Qwen model. Well, to understand exactly why the interventions backfired in those cases, Table 22 analyzes the timing of the failures. It reveals that 100% of the regressions stem from early step disruption. This occurs when the critic interrupts the agent during the very first 0 or 1 steps of a trajectory that was actually proceeding correctly. Effectively, the intervention causes the agent to second-guess itself right at the beginning, whereas mid-trajectory interruptions accounted for exactly 0% of the problems. Wrapping up, the big takeaway is that a highly accurate critic doesn't guarantee a more reliable agent. In fact, unless the baseline failure rate is already high, proactive intervention often disrupts valid solutions rather than fixing errors. The author's 50-task pilot provides a practical guardrail to detect this risk before deployment. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.